This is the third video in a series of 4 videos on backpropagation. Knowledge of the chain rule and its working handled in the second in the series is essential to follow this video. Consider the case where we have more than one hidden layer. We have already seen how to calculate the gradient of the error with respect to the weight between the last hidden layer and the output layer given by dow error rho by dow of the weight WH2O between layer H2 and O. It is delta O into the output of node H2. In the previous video, we found the gradient of the error between the input layer and the output layer. Based on that, the gradient of the error with respect to the weight between the hidden nodes H1 and H2 is given by dow error rho by dow of the weight W H1 H2 between layers H1 and H2. It is delta H2 into the output at node H1. To calculate the error with respect to Wi H1, we use the chain rule because error rho is a function of out H1, which is a function of net H1, which is a function of Wi H1. There are 3 partial derivatives to be calculated. The first partial derivative is from error O to out H1. But to get to out H1, we use the chain rule between error O and netto and out H2 and net H2, and net H2 and out H1. This is shown in the figure. The partial derivative of the error with respect to hidden layer H2 is delta O into WH2O into sigma dash of out H2, which is delta H2. Similarly, the partial derivative of the error with respect to net input net H1, hidden layer H1 is delta H1 given by delta H2 into weight between H1 and H2 and sigma dash of out H1. This delta H1 is multiplied by X and it gives dow error rho by dow Wi H1. Let us increase the number of hidden nodes by 1 to understand the pattern. The error with respect to the weight between the hidden layer node H3 and node O is the product of delta O and output at H3. The error with respect to the hidden node H2 and node H3 is the product of delta H3 and the output at H2, where delta H3 is in turn a function of delta O, the weight between H3 and O, and sigma dash of out H3. Continuing in this fashion, the error with respect to WH1 H2 will be delta H2 into out H1, and the error with respect to Wi H1 will be delta H1 into out I. The pattern has now become obvious. Delta Hi with respect to any node Hi is the product of delta Hi plus 1, the weight between Hi and Hi plus 1, and sigma dash of out Hi. Now that we have found the recursion, let us formalize and write the generalized algorithm. Let L0, L1, etc. up to Ln be the n layers, where L0 is the input layer and Ln is the output layer. Let H0, H1, etc. up to Hn be the hidden nodes. Assume only one node in each layer. Let Wij be the weight between node Hi and Hj. We initialize the weights and bias randomly, and the weights are given by W01, W12, etc. up to WL x minus 1, Lx, and bias B1, B2, etc. up to the bias at layer X. The input is initialized to X and it is given by out H0. At each node, starting from the first hidden layer L1 to the output layer Ln, we calculate the net input net Hx as W x minus 1 x into out Hx minus 1 plus Bx. Similarly, out Hx is equal to 1 by 1 plus e power minus net Hx. This is under the assumption that we are calculating the net input and the output at layer X. As the first step, calculate the error at the output layer. The error, or the partial derivative of the error with respect to the weight, is given by delta O into out hn-1. Remember, in the notation used here, O and hn are one and the same. Similarly, the partial derivative of the error with respect to the bias is given by delta O, where delta O is equal to minus of T minus auto into 1 minus auto. Now backpropagate the error from Ln to L0 using the chain rule. We get delta error O divided by delta of the W between layer X and layer Y is delta Hy into out Hx. Similarly, the partial derivative of the error with respect to the bias is delta Hy, where delta Hy is equal to the delta of the next layer multiplied by the weight between layer Y and layer Y plus 1 and sigma dash of the out at layer Y. If X and Y are two adjacent nodes, then we update the weights and bias as Wxy is equal to Wxy minus eta into the partial derivative between the error and the weight Wxy. Similarly, we update the bias. Question time. Find the gradient of the error at W1, W2, W3 and W4 for the given architecture. Remember, perform the forward pass and backpropagate the error through H1 for W1 and W3 and through H2 for W2 and W4.